All right. Hi, everyone. My name is Ahmed. I'm a product owner at Bloxico. I think some of the people here know what Bloxico does exactly. We have some of my colleagues who already presented some topics in Web3. So I will go ahead and discuss today something very, very controversial, which is the interoperability dilemma within the Web3 ecosystems in general, and which what we call trustless bridges. So the question that we're going to try to answer today is, are these trustless bridges the ultimate interoperability solutions? So is it really or is it not? So we're going to discover that in more details. So we're going to go ahead with the agenda. So today we're going to talk about the problems with the current bridging infrastructure. So we have optimistic verifications, we have what we call light client protocols that run these bridges, we have MPC systems and trusted third-party custodians, such as all the bridges that most of the users in Web3 use. Then we're going to focus on light client protocols. So that's what really this presentation is all about. It's all about light client protocols and their advantages and how can we use them in bridging multiple ecosystems with different consensus mechanisms, of course. Then we're going to take a sneak peek on communication protocols versus optimistic verification. The only reason for this is I know that a lot of you will mention Nomad, because a lot of people think that Nomad is a trustless bridge, and with the recent attack, it appeared that maybe it is, maybe it's not, so we're going to discover that and compare it to certain communication protocols such as IBC, the interchain, the inter-blockchain communication system on the Cosmos ecosystem. And then we're going to have a discussion in a term of Q&A, just some kind of a friendly discussion. Maybe if I don't have the answer, some of you might have, and we'll go ahead with that. So the way that we're going to do this is just not to waste a lot of time. I'm going to present the full presentation, and then we're going to have a Q&A. But if there is some pressing question, please go ahead and ask it in the middle of the presentation. So what is the problem with the current infrastructure? Mostly we're focused on trusted bridges and trustless bridges. Trusted bridges, we have third-party custodians that are validating all the transactions, so we put our trust in them to resolve the conflict between the network through hard forks. And of course, they're very, very easy target to multiple exploits. And even the relay infrastructure as well is still controlled by multiple insiders. And through that lock and release mechanisms, we don't really know what's happening in there because we're entrusted them with our assets. But when it comes to trustless bridges, some people might think that that they don't have an actual drawback, that if we ensure trustlessness, that nothing wrong is going to happen. But that's farther from the truth, because we still ensure trustlessness, but we don't achieve extensibility, meaning being able to be deployed on multiple chains, for example, like a plug and play. And of course, we have finality issues. If you're trying to bridge multiple two ecosystems, two domains with different consensus mechanisms, there is a lot of problems with the domain runtimes, and that's what we call it, like the finality issue in general. And of course, it's a much more complicated relay infrastructure. If you're going to run trustless bridges through light clients, for example, your relay infrastructure will consist of relayers that run full nodes of both chains and, of course, relay the packets of proofs between these two different chains. And of course, their vulnerability to Byzantine and Eclipse attacks. They are not, if you ensure trustlessness, doesn't mean that you ensure security in general. So let's go ahead and kind of discuss my favorite topic, which is the interoperability trilemma. This kind of sums up all what you need to know when it comes to trustlessness, when it comes to interoperability protocols in general. So this interoperability trilemma states that interoperability protocols or bridges in general can only have two of the following properties. So let's go ahead and first of all try to define them. So trustlessness, meaning having the equivalent security to the underlying domain. Extensibility, meaning being able to be supported on any domain, and generalizability, of course, being capable of handling these arbitrary data between across domains. So if we try to map most of the bridges that we have right now in, let's say, the Web3, the blockchain ecosystems in general, mostly are MPC systems where you ensure generalizability and extensibility, which is very easy to do, since you have some bridges that bridge different chains with different value propositions and different consensus mechanisms. So it's not just like Nomad, which is like only for EVM chains. You have bridges that touch more than just consensus mechanisms, which is MPC systems in general. But when we talk about trustlessness, we talk about two distinct solutions to this bridging trilema, which is either you bridge through light clients or atomic locks. And today we're going to talk about light clients. And as you can see here, for example, we have Nomad and IBC, because these are the bridges that kind of use light clients. But Nomad doesn't really use light clients, and we're going to discover that as we go on with this presentation. So for light clients, we can ensure trustlessness because we're relying on light clients that are connected to full nodes on the chain. So we don't need to trust the chain in general. We just need to store the headers of different blocks on the blockchain, relying on the full nodes. And of course, we can ensure their generalizability because once you design that light client, it will be able to handle these arbitrary data between both domains. But I would argue that IBC, which is the Inter-Blockchain Communication Protocol on Cosmos, has achieved in some degree extensibility. So we are seeing a lot of solutions that are using IBC to bridge chains not only to the Cosmos ecosystem, but for example, between Polkadot and Near. So it's really quite revolutionary what they have done with this protocol. So as I said, we're going to talk about light client protocols. So the challenges and the advantages of using light client protocols to bridge multiple ecosystems with, let's say, different consensus mechanisms. And of course, bridging through them has, various advantages because, as we know, light clients do not need to run 24/7, does not need to interact with the blockchain directly because they use full nodes as intermediary, and of course we minimize the trust since we don't need to trust the full node as we are relying on the block headers and in particularly Merkle root tree. And to those who don't know what the Merkle root tree is, it's some kind think about it as a fingerprint of all the information that are presented in the block. So assuming that the majority of, let's say, validators or miners are honest, the block header and therefore that fingerprint is the fingerprint they contain is assumed to be valid. So that's why we kind of minimize the trust needed for these light clients when it comes to the full nodes in general. So those were the advantages, It's pretty big advantage, especially when it comes to storage. Anybody who used, like full node wallets such as Daedalus knows the pain that you can, that you can endure trying to sync with the blockchain. For example, this laptop, would take, if I did not sync with the blockchain in like 2 or 3 weeks, it would take me 1 day for that wallet to sync fully with the blockchain. So light clients, provide amazing services and will allow us as developers and as product related people to find solutions to interoperability and to storage in general. So what are the challenges? This is literally my cheat sheet. If you're trying to develop a bridging solution through light clients, literally these are the 4 things, let's say 3 things that you need to see from the beginning. So the first thing that you need to see is take both domains runtime and check if they support the same signature. Because at the end of the day, light clients will need to verify these signatures. So if you see that both domains do not support the same signatures, then that's your first hint that this bridging solution might not work. And of course, you would need, in order for you to make some changes within the runtime to make these signatures as precompiled, you have to go through a governance process, which we all know might take a really, really long time. The second thing is, okay, domain runtime incapability in terms of missing valid proofs. So each blockchain or each domain have different structure to their blocks, different structure to the header. So you might be missing some proofs that are needed for the light client to function properly. And when I say function properly, I don't mean like liveness, which means like to make sure that your system does not stall. But how can you ensure security? So additional proofs that you will be needing for your light clients and for relayers to relay these packets of proof across these two light clients on these different domains. And of course, one of the challenges that we have is an economic challenge, which is, since we need to validate these transactions, how are we going to validate them? Are we going to validate them singularly or in a batching mechanism? If you're going to validate these transactions in a singular manner, you're going to go bankrupt really, really fast. But the solution to this doesn't need to be an alteration to the domain runtime. Rather, it's a challenge in itself that you would have to make an endpoint that would batch these transactions and validate them. And of course, the biggest challenge of them all is if let's say, the community agrees that we're going to make these changes to the runtime, then of course your solution has to be viable and not put the underlying domain, the underlying blockchain, to some security risks through these changes to their own runtime. So if you like tick all the boxes, 1, 2, 3, and you see that you don't have any problem when it comes to these things, then you will be sure that you will ensure the liveliness of your chain, of your solution, meaning that, okay, I know that my bridge is going to work, and now I have to be concerned about its security. So, as I said before, since light clients relies on, let's say, headers to verify the state of a chain on another chain, I want us to take just some kind of a deep dive into blocks, headers, and these proofs that the light client needs in order to verify the state of a chain within another chain. So blocks are consisted of headers and transactions that you can see. It's very simple. Now, the size of a block might vary from one domain to another, but luckily the header size is fixed within the same domain. So we can see, for example, in the case of Bitcoin, the header size is 80 bytes, and while Ethereum, it's 508 bytes. But when we look at the header itself, it's really different. Maybe I should have put another example here of, for example, proof of work, for a proof of work chain, how the header actually looks like. So you have different informations within this header, and some of these information would be vital to your light clients. So light clients, they rely on transaction root, state root, consensus proof, and finality proofs. Now, as you can see here, the finality proof is not provided within the header, so I would have to acquire it and request it from the full node as an extension of the header. So if I see that, for example, my finality proof is not provided within the header, it's an easy process to request it, from the full node itself, especially for proof of stake consensus mechanisms in general. So I'm going to go ahead and talk about each one and every kind of these proofs that are needed for the light client in order for it to ensure the liveliness of your interoperability solution. So let's go ahead and talk about the transaction root itself. So as you can see, the transaction root is nothing but a cryptographic compression that allows us to verify that some of the data that originated, that the origin of the data was compressed by the wave Merkle proof, in a way that if we're trying to relate the K root here, highlighted in black, to the original root on top, and we see that our Merkle tree here is consisted of 16 nodes, let's say, then we can see that we would only need 4 of the underlying hashes outlined in blue in order for us to prove and reconstruct the original root hash that K was indeed part of the original Merkle tree. So this is nothing but it's just a compression of the data, because at the end of the day, you have to think about the storage requirements that are needed for your light client. And since you need so many proofs, you have to find a way to compress each and every one of those proofs. And the best way of them all is through Merkle proofs. So you take your Merkle tree, you have logarithmic base 2 of the tree height, which gives you how many of these hashes that you need in order for you to reconstruct the original root. So logarithmic base 2 of 16 in this example, the tree height is 60. You would know that you would only need 4 hashes in order for you to reconstruct and prove that, for example, one of these roots is indeed part of the original Merkle root. So we talked about transaction root here. Let's talk about state root. Now, state root, we're still doing a cryptographic compression. So state root is kind of the same as transaction root, but in this manner, it's not. It's comprised of the list of keys and values. And when we say keys and values, we say contracts. We say blockchain subsystems such as consensus protocol storing the list of authorities and their stakes, etc. So by compressing this data, we get some kind of a Merkle root, and we retain the ability to check the existence of some keys and values. So as I said, think about this as the consensus protocol storing the list of authorities and their stake generally in proof-of-stake consensus mechanisms. And still, we're still using some kind of a compressed data in order for us to ensure that our light clients is really light in terms of storage, let's say. Now, when it comes to consensus proof, we would think that this is the last thing that we would need. If the chain comes into consensus on, which miner or which, let's say, validator has been chosen by the chain itself, then we would be 100% sure that the blocks are final, but that's just further from the truth. But here, let's take some kind of a peek on the consensus proof and their differences between different consensus mechanisms. And here, of course, I'm going to keep everything simple. We're going to look at proof of work consensus mechanisms versus proof of stake consensus mechanisms. So here on the consensus proof, as you can see is nothing but the nuance that satisfies this equation. We set the difficulty and the threshold to be adjusted to the network. So we know that this function, we rely on the hash function, which cannot be brute forced by verifying the consensus proof. And it's really cheap and quick. As you can see, there is just one equation that needs to be satisfied through a nuance, and then you will have your consensus proof. But this consensus proof, as I said, does not ensure the finality of the block itself. It only ensures liveliness. But consensus proof for proof-of-stake protocols is usually via VRFs, verifiable randomness functions, where we have this equation. We have each validator of the network would kind of generate a public and private key. Then the validator submits the public key to the network and keeps the private key, of course, for themselves. And the network, of course, uses this VRF algorithm to generate a random number and publish it along with the proof that this number was actually produced using the validator's public key. Then the validator themselves can verify that the proof is valid and that the number was indeed generated via their public key, and therefore the validator with the highest random number will get selected to create the next block. So we can see how different is providing consensus proof between different consensus mechanisms. This is just the difference between proof of work and proof of stake. God knows what are the requirements for other consensus mechanisms. But when we kind of take a deep dive into this, like, what does it mean having a consensus proof? Does it mean that I'm 100% sure that my block is final if the chain comes into consensus. So not really. Consensus proof only ensure liveliness. And we say liveliness meaning, the system does not stall, and that's it. But of course, we cannot guarantee the finality of these blocks because, we have competing blocks of the same height. We're talking about Byzantine fault-tolerant systems. So this, this issue might arise with blocks of the same height coming to compete with this block. So what we need is to find a way to finalize the blocks, to be 100% sure that the header that I'm using for my light client is actually final. How can we do that? Now, this is where kind of modular domains and monolithic domains, monolithic structure of blockchains kind of differ. So you can see, for example, in the case of Polkadot, you have, modular approach. You have Babe, which guarantees liveliness. Grandpa guarantees safety and finalizes the block. And whatever you would need, if you even need to compress that data even more and provide, let's say, ancestry proofs, then you can do that through palettes. You build a palette that can, provide you with a compressed, let's say, finality proofs. And, it's kind of gives us that deterministic finality versus the probabilistic finality that we work on with monolithic blockchains. And in general, it's for proof of work consensus mechanisms. Now, let's talk about finality proofs. So since the finality proofs on most proof of work consensus mechanisms is nothing but the nuance. And as we saw before, the nuance is also our consensus proof. So you have the nuance, like same information as two proofs. So it presents your finality proof and your consensus proof. So what do I need in order? What do I need to provide to make sure that this finality is actually true? So what we need is to kind of make sure that we have a time threshold in order for us to ensure that blocks of the same height, like competing blocks of the same height, would not arise, and therefore I would not risk my block being reverted or the whole chain being reverted through hard forks. But in this way, you would have to store n headers in order for you to be able to verify n-1 header. And n-1 is really optimistic because you would need to store much more than that in order for you to make sure that this block will not be reverted anytime soon. So in this way, we're still running with proof of work consensus mechanisms. We would run again and again into storage challenges. But when it comes to finality proofs on proof of stake consensus mechanisms, and in this particular example, we have Polkadot's finality proofs. We have finalization rule, which is you need more than 2/3 of the stake to finalize the block. We have different two protocols, one that ensures the liveliness, one that ensures the security of these blocks. We have Babe and Grandpa. So these finality proofs will kind of not be included within the header, but you can request them as an extension of the header from full nodes. And of course, it's nothing but a signature of the known authorities that stake their tokens and that they would risk to be slashed in case of any malicious activities. And in that way, we can ensure the security as well, not just the finality of these proofs. And of course, as I said before, it's just the signature of this data from 2/3 + 1 of the known authority sets under the security assumption that less than 1/3 of the authority set is malicious. So this is in a nutshell what finality proofs are in the proof of stake consensus mechanism. And you can see the huge difference between that and finality proofs on proof of work consensus mechanisms, in particularly here in Bitcoin. So the problem that we run into every time we talk about finality proofs are really storage requirements for your light clients. But if you had a modular approach, if you have a domain that have a modular approach, such as Polkadot, and I'm sorry if I'm bringing Polkadot all the time, but really, like, they're pioneers when it comes to, providing as much more detail as possible from blocks and from their headers to light clients. So we can see that we can, instead of sending these finality proofs to the light clients, we can even go a step further and ensure the security, ensure that these finality proofs, these headers, and these blocks would not get reverted. And that's through ancestry proofs. But still, ancestry proofs, it's always about storage. So most finality proof would require these light clients to be aware of the full chain of headers in order for them to ensure that, to verify the state of a chain within another chain. So what we actually need is a smaller size of ancestry proof. You can see, in this example, in order for you to verify the state of one header, you need, as I said before, n-1 headers, and to prove that that header is actually the parent of, let's say, 10 headers in front of it. And that's not really a solution, for a light client, for using a light client to bridge between the, multiple ecosystems. But we can actually use what we have used before when it comes to transaction routes, But let's go ahead and do some quick math. Let's say if I'm going to provide ancestry proofs for a tree that is with 1 million blocks, for a blockchain with 1 million blocks. So if we do logarithmic base 2 of 1 million, we have a tree height of 20. That means you would need 2,097,151 nodes in that tree. That's a gigantic number for a blockchain that just has a million blocks. So what we need is a different tree structure, So we have to still compress this data even more. And the way to do that is through what we call highly efficient ancestry proofs. And these highly efficient ancestry proofs can be achieved through Merkle Mountain Range. So Merkle Mountain Range is nothing but pruning this tree, But in order for you to prune it, you have to prune it in a way that you would be able to preserve the, how to say this, preserve the root hash of each subtree. So we have, for example, this is our main root, and these are the subtrees. So if I'm going to prove, for example, in this particular example, we want to show the inclusion of node at position 8, highlighted in green, in the peak of our position 15, which is yellow. So we need the hashes of these sibling nodes highlighted in blue in a way that 9, for example, proves that 8 is in 10, 13 proves that it's in 14 and therefore in 15, and 7 proves that it's in 15. So if I'm working with the node at position 8, I would automatically prune all the subtrees on the other side. I don't need them. I don't really need them in order for me to reconstruct this Merkle tree from this position. But the one thing that I need to do is preserve the peak hash of this subtree. If I do that, that is the only thing that is the only rule that you need to keep in your mind while pruning this tree. And if we do that, you can see that we preserve so much data. This is nothing but a simple example. Imagine a tree of like we said, like in the previous example, of tree of 20. Imagine how much data you would save providing these highly efficient ancestry proofs. So what is the conclusion in general? So as I said, light clients require these packets of proofs from block headers that consisted but not limited to transaction routes, state root, consensus proofs, finality proofs, and in some cases ancestry proofs. And we can see that some of these proofs kind of collide. So consensus proofs and finality proofs in proof of work consensus mechanisms are the same thing, which is the nuance. Finality proofs and ancestry proof can be finality proofs in the proof of stake consensus mechanism on modular blockchains like Polkadot can be enhanced into what we call ancestry proofs through Merkle Mountain Range, and therefore we kind of mitigate the problem that we have with storing these kind of data, and not just storing these kind of data, because you still have to relay these data through the relayer infrastructure from one light client to another. So it's not just, your problem is not just with the light client running on a specific chain, but with the relayer infrastructure that is going to relay these packets of proofs to the other chain. And this is, as I said here, this is just the first layer of challenges that you would face when developing these trustless solutions. You still have problems with the relayer infrastructure. It's very complicated. if you have to run full nodes of both chains that require, immense amount of, good hardware in order for you to be able to do that. And of course, with different domain runtimes, if you're really persistent and you want to, let's say, bridge two domains with different consensus mechanisms and different runtimes and have different signatures and none of them support the same signatures, then you should really try to give up if you don't have the support from the community itself and the support from, of course, the development team to be able to render these signatures as precompiled within the runtime of this underlying domain. And of course, the other challenge that you would face is to keep this light client as light as possible. And in the case of proof of stake consensus mechanisms in modular blockchains, you can always do that through developing different protocols that would run on, for example, on your finality gadget, such as Polkadot. So Polkadot have Babe, Grandpa, and on top of it they have the Beefy protocol, which provides ancestry proofs to light clients in the most elegant way possible that you would think. It provided light clients with a true breather, when it comes to ancestry, when it comes to finality proofs, because when we talk about ancestry proofs, we still talk about finality. And as I said, so this is where really modular blockchains really shine. So hats off for Polkadot, honestly. So here I'm going to talk about communication protocols versus optimistic verification. Since we've already saw what we actually need in order for us to bridge different chains with different consensus mechanisms, what kind of proofs do we need so that it's mind-boggling the amount of data that you would need. But I wanted to keep it a little bit off of that subject because I knew some of you might ask about, Nomad in general. Some people think that it's a trustless bridge, but in its structure, it's not actually trustless, it's optimistic because it does not run with light clients, but rather it uses smart contracts and unidirectional kind of bridges from the underlying chain to the destination chain. And we can see the big differences here between optimistic bridges and communication protocols that are made in a way that they serve a single purpose, which is to use light clients to bridge different ecosystems with different consensus mechanisms. And in this way, we have the one and only IBC. So what is IBC? IBC is a protocol that was developed by the Cosmos ecosystem. It's connecting the Cosmos hub with the different chains and the Cosmos ecosystem. It is important to note that the Cosmos ecosystem is very different than Polkadot ecosystem or Kusama ecosystem in a way that in the Polkadot relay chain, provides security to the underlying parachains or parathreads. But in the case of Cosmos, that is not the case. They run on different consensus mechanisms, but they're still built on the same SDK, which is the Cosmos SDK. So in this way, you don't have any problems with supporting different kind of signatures, and it's very easy to deploy light clients and bridge these ecosystems to the Cosmos hub itself. So as I said, the fundamental of IBC is very clear in itself. You're relying on light clients to relay packets, to relay these packets of proofs to other chains, and therefore, ensuring both the liveness and the security of this bridging solution. So just in general, it's just packets of proofs being relayed from one chain to another, and it's not a unidirectional bridge. It goes both ways, from chain A to chain B or from chain B to chain A, and the assets do not actually leave the original chain, but rather they get locked on the original chain through a mint and burn process. So if you're sending from the original chain, your assets will be locked, and the same amount will be minted on the destination chain. So this this protocol is completely permissionless in a way that anybody can run relay infrastructures. It's very complicated though. I mean, the software is available to everyone. The only problem that you would have is the hardware itself. So that is when we talk about interoperability protocols, usually it's about security, but a lot of people do not pay attention to the storage requirements or to the hardware requirements in order for you to be able to run a relayer infrastructure for these two light clients in order for them to communicate seamlessly. But when we talk about Nomad, we talk about optimistic bridges. So this bridge works through optimistic verification, and it does not use light clients. We have two different smart contracts, one on the underlying chain and the replica on the destination chain, and we're relying on some kind of watchers that guarantees only the liveness. So they go through the assumption that if one of n watchers proves that is still honest, then our bridging solution will still be sound and it will not stall. But as we saw that, a simple bug, generic proof on the replica chain, and of course it cost them, I think, 160 million, something like this. The bridge was completely decimated. So it's a very different solution than interoperability protocols such as IBC that relies on light clients. Still, we have a lot of problems when it comes to trying to connect to domains through light clients. But for sure, one of them will not be about liveliness, about the system not being stalled. That is the last thing you would think about. It's more of 51% attacks and Eclipse attacks that might occur on bridges using light clients. So it's a completely different thing, optimistic bridges and light client bridging protocols such as IBC. So what's next? The next thing we need to ask ourselves is the problem with light client-based bridges, and this has been known since the beginning. So what must we ask ourselves at this point that we know what proofs do we need, what are the challenges that we face in terms of hardware, in terms of storage, in terms of keeping that light client as light as possible. So the first question would be, how does one run an on-chain light client, but rather how does this on-chain light client respond to Byzantine systems? When we talk about Byzantine systems, we talk about 51% attacks, Eclipse attacks, and these different attacks that might render our bridging solution completely obsolete. So does it roll back the state of the event of a Byzantine attack? Which fork will it choose? And how can the security of these assets be preserved in this Byzantine state of the source chain? And the other question that you need to ask yourself, do I stay tied to cryptographic soundness, or do I need to play another game theory? When we say game theory, we say provide an additional threshold, an additional breathing period for the light client to be 100% sure that these packets of proofs that he's sending to the other light clients are actually sound and final, and there is no way of different blocks with the same height occurring, and these packets of proofs would be reverted. And that's about it. Thank you so much. Now we'll go ahead with thank you. We go ahead with a little bit of discussion and Q&A if anybody has some question.
Okay, can you hear me? All right, if you can just tell me in the IBC example, okay, we have all those proof of headers, ancestry proofs, finality proofs going to the relayer along with the message. If you can tell me what stops the relayer itself, because it goes from chain A to relayer to chain B, what stops the relayer of kind of tampering with the proofs and with the message itself?
All right. So in the current infrastructure, I'm not talking about IBC. If you're going with just light clients, and you have all of these different proofs, ancestry proofs, you provide the light clients with everything that it needs, you still run into a problem where, some validators might go like malicious, and in a way that they don't participate in the P2P swarm, so they don't gossip, because the light client cannot participate in the P2P swarm. It can only get that information from the full node. So the only way to mitigate this is to allow the light client to be part of the P2P swarm. So it can gossip with the full chains and see if one of the if that information is malicious. Other than that, there is no other solution. You have to make your light client be a part of that P2P swarm. I hope that answers the question.
Hi there, thanks for the presentation. I have a question that you may have already potentially answered throughout the presentation is how do you prove the validator set? So proving consensus after you prove the validator set is easy, but how do you know that the data that is passed by relayers to the other chain and has signatures with it, how do you know that those signatures are from the current active validator set on the other chain?
From the current set of active validate, as I answered Andrea's question. So if you don't have the light client participate in the gossip, so these validators, after finalizing the blocks, they need to gossip in order for them to prove the finality of that block. In a way that the light client itself is not part of this gossip. So in case that let's say the full set of validators try to send these malicious messages, these malicious proofs to the light client, there is no way for him to know that these are malicious, because he trusts the full node to give him these information. So the only way is for the light client to be part of that P2P swarm. Okay, so this is kind of like 51% attack that after, if it goes through, it becomes Eclipse attack. If it goes through, it becomes long range attack.
So do the light clients have the full history of block headers? Because from your presentation, I think I understood they have like the logarithmic number of block headers.
The logarithmic number, they don't, but you have to, there is another protocol. So for example, in the IBC example, they had to mitigate this through allowing the light clients to be able to not just get the information from the full nodes, but also to participate in the, let's say, consensus proof, the consensus process, without having to download the full ledger. Without having to download all the headers in a certain chain. So that's why.
Okay, so I'll give you an example. We are at block height 50, and in block height 50, when we transition to block height 51, we have consensus that the validator set changed. And how do you prove that, like later, I don't know, when you're trying to validate block 60, that there's a new validator set that was changed in block height 51? Because if you do logarithmic block headers, you may not contain the information from block 51.
Okay, so maybe the only answer to this would be Fisherman, because it's still, as I said before, like light clients, there is no way for these light clients to like ensure that these proofs, these packets of proofs that are provided by full nodes are actually true. So we rely on this. This is why trustless, So you rely on the security of the underlying domain. If the underlying domain fails, then automatically my light client is going to fail. The only thing that I can do is provide a threshold, meaning some timing for the fishermen to do their job and to see that, for example, some of these validators are trying to trick this light client with fraudulent proofs, for example. But there is no way for the light client to be a part of that consensus, if you know what I mean.
I kind of get where you're going, but the thing is, like, it's trustless because you have to trust both chain A and chain B, but the consensus mechanism did not fail nor on chain A nor on chain B. Like, they're in consensus on the state that block height 60 or even 51 and everything. I'm just asking, how does the light client on the other chain with the logarithmic number of headers prove that it's on the correct state and that the validator set changed? Because the relayers are there only for liveness, and they cannot impact the security of the protocol in any form. So they cannot prove something that is not in consensus on either chains.
Okay, but they will still have to keep, as a relayer operator on IBC, you still have to keep the full ledger of both chains. So
yes.
So if you have the full ledger of both chains, meaning that the destination chain would be able to verify that those proofs, or I don't know, like this the validator set is valid from the relayer infrastructure itself. Does not have to go and communicate with the light client on the other side. You still have. This is why, like, I didn't. It's just about timing. If we go deeply into IBC, it's another story. We just wanted to kind of present all the problems that we have with these solutions. But how to mitigate these challenges, it's a whole other story. So the relay infrastructure is completely different. You still have to run both full nodes of both chains in the as a relayer operator in order for the destination chain to be not 100% sure, but securely prove that these packets of information sent from these light clients are actually valid. But maybe next time, I would love to present again and go through IBC and how they mitigated all of these. It's all about like Byzantine fault tolerant systems. It's just how can we mitigate all of these risks on Byzantine fault tolerant systems. But to go into detail into that, maybe next time. But it's still, you have a relayer operator that have a full node of both chains.
Thanks. Anyone else?
Thank you.